Hello everyone, welcome to the next video on design of FC TCR. In the previous video, we designed the power circuit, then the power measurement blocks and controller to control the gate signal of FC TCR. In this video, we are going to see how we can do the measurements for this. So what are the graph we have to see and what are the readings we have to note down. Uh, so in this case, you can observe over here, this is power GUI block is needed to simulate the power system model. So you can search for a power GUI and you can select this power GUI block in your system. So already I have taken this power GUI block to simulate the system. Now I want to measure I will take the from block. Okay, in this from block, I want to measure the voltage and currents. So voltage and current of the source. So let me take the VS over here. Okay, so I'm adding the measurements block. So let me zoom in this area so it will be clear to you. So VS now, sorry. Okay, so this is the block of IS. Now we need to measure the reactive power supplied by this source. So we'll take again the from block. So this block is of QS. In the similar manner, I will copy this for VL load side voltage. Then I will copy this two block. So let I will choose this as IL. Okay, and this as the load reactive power. In a similar manner, I need the compensating voltage. So VC. This is IC. And this is QC, that is reactive power supplied by the compensator. So I need these all graphs. So I will take a scope. Okay, in this scope, double click on this scope. I need a 3-axis over here. So let us take 3-axis layout. I will choose vertical layout. Okay, so likewise these 3-axis are chosen. Increase this, sorry. Okay, let me zoom again in the measurement area. So let me increase the size of scope. Let us connect the scope. Drag the this similar scope over here and connect. You click on this line, so it will be get connected. Similarly, okay, all these are connected. Now, I want to display the power factor. Okay, already I have displayed the source side power factor and load side power factor in this window. You can observe here, source side power factor and load side power factor. Okay, now one more measurement I need in this circuit, that is the current supplied by the TCR, because harmonics are generated there. So go to in the FC TCR system. In this FC TCR system, take the block of current, okay, current measurement. Join this current measurement block in series with your TCR model. Okay, TCR model, and take a block of go to, connect over here, and sorry, I'm connecting it wrong position. Okay, so this must be connected here, and rename this go to block as ITCR. Okay, so this is the ITCR. Make this global. Okay, now this is the current ITCR. Go up, come into the main model. I want to display this ITCR and firing angle also. So again, I will take the block of from. I want to display the firing angle. So we have calculated the firing angle in the controller circuit. So here you can observe in the controller circuit, which is at bottom. Here we are getting the firing angle at this instant. Okay, so after the PI controller and saturation block, we are getting the firing angle which is in degree. So I will connect one block of go to over here, and I will join this with this, double click to this, and this is the firing angle alpha. Make it global. Okay. So if you create a circuit systematically, then it will give you it can you can easily simulate. Otherwise, the connection understanding of the connections will become difficult. So here I want the alpha, and I want the ITCR current also. Okay. Now here I need scope again. So I will copy the same scope which is above. Here there are three axes. So double click to this. Okay. Make the number of axes is equal to 2, and layout, in the layout only choose 2. Okay. One more thing here we have to do in the setting, because we need to analyze the harmonics of the TCR current. So go in the logging data. Here you click on this, and here you can type ITCR. Okay, ITCR, and it must be structure with time. This data type must be structure with time. Okay, so now again I will reduce this size, connect this here, connect this here. Okay, now everything is ready. We are ready to simulate. So let us check first how much uh, power I have set here. I have set the inductive power as 13,333 VAR. So let us make it 10,000. Okay, or you can start the readings from 1,000. Okay, so first I will take the reading from, or one, not 1,000, we'll take start from 2,500. Okay, so 2,500 will start the reading. Whether this will supply that much reactive power or not, that we will check. Okay, run this. Okay, it is running. Okay, 0.8, 1.2. You can double click the source side. Okay, let me double click this. Okay, so here, if you see the graph, okay, by vertically zoom. So here you can observe these are the voltages and the current. Okay, so voltages and current you can observe over here. Hello, welcome to the next part. Last time I did one mistake over here. So here I put the AND gate by this at this two location, put the AND gate. So please remove this AND gate and connect the relational operator with the greater than sign. Okay, so make this change in your circuit of the controller. In controller, VC and 0 must be compared. Okay, so that it is not ANDing operation, it must be compared. Now, okay, so PI controller gain is adjusted to, let the PI controller gain is adjusted to zero point 0.1 and 0.05. Okay, let me check what I have adjusted in my previous simulation. Okay, so it's 1 and 1.01. So coming into this block, these gains are set as 1, 1 and 0.01. Okay, so I have set this PI controller gain. Now again, I will start running the circuit. Let's check whether I'm getting the output. Okay, or not. If not getting the output, then PI controller is must be tuned again. So if we check at this instant firing angle. So firing angle is switching between 0 to 180, means 90 to 180. So means our PI controller values are not adjusted properly. So let us tune the PI controller value. So meanwhile, I will pause the video and I will tune the PI controller value and I will tell that value to you. Okay, so I'm pausing. Hello, welcome to the next part. In this part, uh, in a previous part, I have paused due to tuning problem of the PI controller. Now the PI controller are tuned. So after the in controller block QS block, you connect a low pass filter with the transfer function of 1 upon S plus 1. So you connect this low pass this in a controller you connect this low pass filter, so it will filter out the harmonics low and it will only pass the low pass, that the DC signal will be passed only through this controller. Now in a PI controller you keep this PI controller values to, okay, zero point 0.1 and 0.001. So proportional control is zero point 0.1 and integral control is 0.001. Now let us run this model. So before running this model, let us have some settings in the solver. So on the right click on the right hand side corner, you can see this ODE 23 TB. So change this setting. Okay, come to here and select the ODE 23 TB. Then go into this solver details and select the maximum step size as 5 e raised to minus 5. Okay, maximum step size as 5 e raised to minus 5. Then first we will simulate the system for the load of 2000 for the load of 1000 megawatt 10,000 megawatt with the reactive power of 2500. Okay, so reactive power is of 2500, and let us run this circuit and observe the firing angle and the current fed by the TCR model. It is compiling. Wait, set this stop time is equal to 1 second. It is sufficient to analyze up to 1 second. Okay, so you can check in this observation here. The power factor of the load is 0.97, whereas from the source side the power factor is 0.999, means approximately the power factor is equal to unity. If we see the firing angle, so the firing angle here you can observe this firing angle is very near to the 100 degree. Okay, so here you can observe this firing angle. So see, this is the firing angle, which is very near to the 99 degree. And this is the current supplied by the TCR. Let us zoom on x-axis. So this is the current supplied by the TCR. Let us observe the source side voltages and currents. Okay, so in this scope, Vs, Is, and Qs. Okay, click on this icon. So you can observe the voltage and current. If I zoom this within this area, the voltage and current are almost in phase, and this source current is get polluted due to the TCR current. The source current is get polluted due to the TCR current. Here you can observe the voltage and current are in phase, whereas the reactive power fed by the source is almost equal to 0. Now let us observe the load side, whether the load is getting the required reactive power or not. Okay, so open the scope of load. Here you can observe the required reactive power is 2500, which you are getting here. Then observe the source side, current supplied by the load, sorry, current supplied by the compensator. So the current supplied by the compensator, you can observe over here. So compensator is providing the 2500 VAR reactive power minus 2500, which is the requirement of load. Now let us analyze the harmonic analysis. So for harmonic analysis, go into the model setting, because some settings we have to do for this. Go into the model setting. In that model setting, you will see one port with data import and export. In this data import and export, this single simulation output is tick over here. Untick this, because unless you untick this, FFT window is not visible. So a data import and export, you untick over here, apply. Okay. Now come to the Power GUI block, Power Graphical User Interface. Come to the app, go into the FFT analysis. If you remember in the last, when I started the video, I stored the current of ITCR in the scope. So let us have FFT of that current. So this ITCR is stored in the scope. The data points are stored in the scope. So you can observe here, you are getting the data points. So let us analyze this signal. Okay, for okay, uh, let me update it. We'll observe for IL. Just a minute. It is not updated in this window. Just a minute. Let me check whether I have stored that data with the correct name or not. Open the scope of this ITCR. Here, go into the setting, go into the logging. So I have stored this with ITCR with the structure with time. Okay, let me run this model once again. You can run this model from here also. Okay, here the ITCR current is appearing. Let the simulation is completed up to the 1 second. Okay, now it is at the end side. Again, come to the power GUI block. So simulation is completed. Come to the power GUI block. After unticking that modeling, now you can see in apps FFT window, I want to analyze the ITCR current. In that second input is my TCR current. I will analyze it from zero point 0.5 second to for 5 cycles. Okay. Then frequency, fundamental frequency is a 50 hertz. Maximum frequency content, which I want to see here, it is up to the 1000. And if I say the compute FFT, okay, so this is FFT is calculated for this red signal, or you can say only FFT window is to be shown. So for this red signal, you can observe the THD is 10.39%, with the fundamental current is 68.27. If you want to see the list of the harmonics, so you can click this list relative to the fundamental, and again click to the compute. So DC component is 0, fundamental is 100%, second harmonics is 0%. third harmonics is 8.38%, fourth harmonics is 0%, fifth harmonics is 4.67%, and the THD in the current is equal to 10.39%. So this we have observed for okay, so let me take a downside. This we have observed for the 2500 VAR reactive power demand of the load. Now let us change the reactive power. We'll come to the maximum side. That is, I will change it to 12,500 total reactive power. So 12,500 means almost power factor is zero point 0.6. If you calculate the power factor, it will be 0.6. Okay, next again we will observe the now see the reactive power demand of the load is more, so capacitors will supply the reactive power, whereas TCR will absorb very less reactive power. So let us check the alpha values and the ITCR. The current by the ITCR may be very low. Okay, if we double click to this block. Okay, let us check the firing angle. Okay, so in this scope, you can observe the current is reduced to well below of maximum value is very less, that is less than the 20 ampere, and the angle is equal to 142. If I observe the voltage and current of the source, so you can observe the voltage and current of the source over here. The reactive power supplied by the source is almost zero. Then if you observe the load side voltage, current, and reactive power, so load is getting 12,500 reactive power. So you can see here it's 12,500 reactive power. Okay, so required amount of reactive power is at the load side, and the compensator will provide the required current. And see, the total 12,500 reactive power is supplied by your minus 12,500 is supplied by the FC TCR scheme. So now let us observe the FFT of this. Again, I will open this FFT window and I will observe this ITCR. I will update this ITCR for input 2. So here the THD is increased to 75.06%. So you can observe for the higher firing angle, that is very low injection of the low absorption of the TCR, the THD value is increased. So this we can record for our purpose. So I have completed the simulation of FCTCR. Hope you have liked it. Only one change you make in your circuit, that in this thyristor you make a snubber resistance is equal to 500 and snubber capacitance is equal to 250 e raised to minus 12 before simulating. PI control value, already I told you that PI control value is 0.1 and 0.001. In this case PI control value. So you can observe the power factor of the source is always 1, whereas the power factor of load is 0.6247 over here. So by this way we can simulate the FCTCR. Hope you like this video. If you like this video, kindly subscribe my channel and share with your friends. Thank you.